Welcome to this explainer. Today, we're taking a hard look into the black box of the future. We hear about artificial intelligence and breakthrough apps constantly, right? But where do those ideas actually come from? Today, we're going to track a truly fascinating journey, the exact pipeline of turning raw science straight into tangible technology. So let's just dive right into the roadmap. We'll start with the research blueprint, hit abstract math and theory, look at parsimony, which is basically doing more with less, explore tech in the physical world, dive into lifelong and causal learning, and finally, wrap up with exactly how science becomes technology. All right, Section 1, the research blueprint. We have to start by talking about the proceedings of machine learning research, or PMLR. This is essentially the ultimate, heavily peer-reviewed catalog of raw scientific discovery. If you want to know what the tech industry is going to be selling you half a decade from now, this is exactly where you look. It's not some glossy consumer magazine. It is the unfiltered, bleeding edge of global computer science. And this archive is literally massive, going all the way up to volume 336 on learning theory in 2026. Just think about the sheer volume of human intellect it takes to produce 336 distinct volumes of cutting-edge research. It holds the literal blueprints for the apps, the medical devices, and the smart grids you'll be relying on 5 years from now. Now, these aren't just dry academic conferences. They represent an incredibly vibrant spectrum of distinct scientific disciplines, all coming together to illuminate the unknown voids of AI. We've got researchers dealing purely in the shapes and structures of data in volume 325, all the way down to engineers figuring out how to make AI control physical robots in volume 331. Every single volume here is a highly specialized gear in a much larger machine, turning together to bring science fiction into reality. Moving on to Section 2, abstract math and theory. So at the very top of our funnel, we have foundational science. This is the deeply abstract math that makes absolutely everything else possible. Look, before you can ask a chatbot to write a poem or have a car autonomously drive you to work, someone has to prove the underlying mathematics actually function without collapsing. Brilliant minds are out there solving incredibly theoretical problems in geometry and topology, which you can see in these real paper titles from volumes 325 and 336. A title like The Embedded Homology of Hypergraphs on Manifolds probably sounds like an alien language to most of us, but in the machine learning world, it's basically the math of mapping out incredibly complex, invisible relationships in data. It's the theoretical physics that absolutely has to precede the engineering. This is really interesting. Notice the stark contrast here between the highly theoretical science on one side and a highly applied, life-saving medical tool on the other. Both of these are peer-reviewed papers born from the exact same research ecosystem. But one is trying to fundamentally understand the mathematical invariance of a network, while the other is benchmarking lightweight models to detect actual medical seizures on deployable hardware. I mean, this perfectly captures our whole journey today, taking raw, abstract science and forging it into tangible technology. Which brings us to Section 3, parsimony, doing more with less. To actually bridge the gap from that abstract math to your everyday devices, we have to make things smaller. We have to make them faster. And that leads us to the optimization phase, discussed heavily in volume 328. In the context of AI, parsimony is the art of extreme efficiency. It's all about frugality. Remember, these theoretical models start out requiring supercomputers the size of literal warehouses. Parsimony is the science of shrinking those massive models down so they can do way more with way less. We're talking about getting them to run flawlessly right on your home computer's GPU or even your smartphone without losing a single drop of their core intelligence. And taking those heavy processing loads and compressing them into lightweight formats is exactly how this science becomes consumer tech. Taking a look at these innovations from volume 328, you see researchers absolutely dedicated to making AI accessible. Tools like LMMQ are explicitly designed so that massive models can be trained on standard consumer GPUs. Concepts like pruning and quantization, which, sounds super intimidating, are really just the scientific methods of cutting away the digital fat. They mathematically shave down the unnecessary data so that AI can literally fit right in your pocket. Let's move into Section 4, Tech in the Physical World. As we move further down the funnel into Volume 331, Learning for Dynamics and Control, we hit this thrilling threshold where digital algorithms finally break out of the server room. Guys, this is where the magic happens. Look at how these dense academic titles translate directly into real-world tech sectors. A paper on physics-informed neural operators is actually laying the groundwork for cutting-edge cardiac healthcare monitors. A study on aggregate flexibility with end-to-end learning that's directly targeted at creating smarter electric vehicle charging networks. It is genuinely awe-inspiring to realize that this crazy abstract math is actively steering cars and monitoring human hearts. But here's the crucial point. Before any AI operates a physical machine, it has to be safe. You can't just plug a chatbot into a factory robot and hope for the best, right? It has to undergo rigorous safety verification science, like this paper proposing barrier bench. Researchers are actively creating intensive benchmarks to evaluate if a large language model can securely operate within dynamical systems. The goal is to ensure it absolutely won't crash in the real world when something unexpected happens on the factory floor or out on the highway. Section 5. Lifelong and causal learning. A physical system isn't very useful if it's completely rigid. An autonomous car or a smart medical device needs to adapt to a constantly changing environment. And these papers from volumes 323 and 330 prove that researchers are actively building agents that don't just solve a puzzle once in a sterile lab. Through concepts like prediction-oriented subsampling, they're teaching AI to continually learn from flowing real-time data streams. They're embedding causal importance, so the AI understands actual cause and effect over time, rather than just recognizing static historical patterns. It's the profound difference between just memorizing a map and actually knowing how to navigate the bustling streets of a brand new city. Finally, Section 6, Science Becomes Technology. We've reached the narrowest part of our funnel, where foundational theory, parsimonious optimization, and physical modeling finally yield a truly usable tool for society. Now, while this specific title, Sono Edit, Null Space Constrained Knowledge Editing, sounds incredibly intimidating to read, let's just break it down. It's from volume 328 on parsimony, and it is actually just the highly advanced scientific foundation for the next generation of seamless text-to-speech software. So when your audiobook narrator sounds flawlessly human, or your digital assistant corrects a mispronounced word perfectly on the fly, this null space constrained knowledge editing is the exact science making that everyday convenience possible. When we step back and look at the whole pipeline, this is the main blueprint you should take away from our explainer today. Every single piece of everyday tech starts as a heavily peer-reviewed abstract theory in step 1. Then, in step 2, it gets logically shrunk down and optimized to actually fit on our devices. In step 3, it's safely integrated into physical reality. And finally, in step 4, it lands right in our hands as a polished, world-changing consumer technology. The pipeline from the proceedings of machine learning research directly to your living room is continuous, and it is accelerating fast. As the spectrum of research continues to light up the dark unknown of artificial intelligence, think about this for a second. If today's deeply abstract math is tomorrow's standard smartphone feature, what impossible technology do you think next year's science is going to unlock? Keep learning and keep looking at those blueprints.